So welcome to my talk. I'm Yuhao from UT Austin, and today I'm going to be talking about GreenWeb, which is a set of programming language extensions for making the mobile web energy efficient. So the web has been an integral part of our everyday life for a very long time. But if we think about the way we access the web, it actually has changed quite a bit. While traditionally we've been using desktops and PCs to access the web, as mobile devices become more and more popular, we're increasingly access the web from our smartphones and tablets. And even on a smartwatch like this, many applications are based on web technologies. So the mobile web is really overtaking the traditional web. And to convince you, let me just show you one piece of evidence, among many others. Now in this figure, the x-axis, I'm showing you the year, which moves forward from left to right. The y-axis shows the overall volumes of web searches, which to the first order capture the overall web usage. And I'm showing you the overall web search volumes over the years from both desktop systems and mobile systems. And as we can clearly see, more and more people are using mobile systems to access the web. And in fact, the inflection point is already upon us. So I think it's fairly safe to say that whenever we talk about the web today, we're basically talking about the mobile web, which is actually great for us end users because the mobile web really enabled a lot more things that the traditional web wasn't able to do. But there's a problem. The mobile web is actually becoming increasingly challenging for developers, primarily because mobile devices as a computing platform are extremely constrained. Mobile devices are slow, they're still much slower than even a laptop today. They rely solely on wireless connections, which are flaky and less reliable. But perhaps the single most important limitation of mobile devices is that they are severely energy constrained, because they do not have a constant power supply and they are limited by the battery capacity. As a result, energy consumption became a serious concern among mobile developers. So there is a great paper published at ICSI this year where the authors surveyed over 400 application developers from companies like Airbnb, Google, and Microsoft. And one of the questions that they asked was, do your applications have energy requirements? And then they classified the responses into three categories: often, sometimes, and never. And as we can see, more than half of the mobile application developers actually do have concerns about the energy consumption of their applications. And just to put that number into perspective, the percentage of developers who care about energy in mobile space is actually much higher than in traditional desktop and cloud computing. So this data really shows that the energy consumption is a serious concern for mobile developers. And not only that, these developers are actually willing to do something to save energy. Now from the same survey, another question that they also asked was, are you willing to sacrifice performance, etc., for reduced energy usage? And again, we see the majority, actually over 75% of mobile developers are actually willing to scale back the performance or to lose usability to some extent in order to save energy. Right, so the problem here really is that mobile developers care about energy efficiency and they want to optimize for it. But on the other hand, their top priority is still to make the application responsive, or in other words, to deliver good quality of service. And these two are the two requirements that are most often conflicting with each other and they create tension. And what a mobile developer really wants to be able to do is to make calculated trade-offs between QoS and energy efficiency. So we propose GreenWeb, which is a set of programming language extensions that will help developers, mobile developers, balance between energy efficiency and quality of service in mobile web computing. And just to put GreenWeb in the context of existing web languages, namely HTML, CSS, and JavaScript, GreenWeb is not adding a new language. We're not radically changing the way developers program for the web. Rather, GreenWeb extends existing languages, in particular it piggybacks on top of CSS. And it turns out that there are various good reasons why we chose to extend CSS, as I'll cover later. But the high-level idea of GreenWeb is that it provides a set of language abstractions that allow developers to express quality of service information of their applications. And then the language runtime that takes the QoS information as hints and tries to save energy whenever possible, as much as possible. By having developers, web developers, and the web runtime work with each other, the overall system can achieve a significant amount of energy savings based on implementations on real systems. And this is also going to be the outline of my talk today. So let's first talk about language abstractions for expressing QoS. So what is quality of service in mobile web anyways? So we really have to understand quality of service with respect to raw performance. So there's a lot of prior work in systems and HCI that all showed that quality of service can be really classified into three regions, depending on the raw performance. Now, at the beginning, the performance is just too slow, the application is not usable. And that's what we call the unusable QoS region. As performance keeps increasing, the application became usable, and then users could get some utility out of it. And that's what we call the tolerable region. As performance keeps increasing, we get into this diminishing return area where further improving performance does not lead to any perceptible QoS improvement. And that's what we call the imperceptible region. Now, this relationship between QoS and performance actually has a deep implication on energy. And let me overlay the energy curve on top of the same figure. In the imperceptible region, as we decrease the performance, we're also decreasing the energy. And this means that we can actually save a lot of energy without hurting QoS. As we enter the tolerable region, this represents a classical trade-off between performance and energy. But as we enter the unusable region, we're consuming negative energy. And I call we consume negative energy because when the application is too slow, users tend to abandon the application or the service altogether. So for example, if a web page takes too much time to load, we are just going to kill the tab and walk away from it. All the energy consumed up until application abandonment is wasted. So we're burning energy without providing users any utility. And that's why we're consuming negative energy. So what this figure shows is that we ideally want to stay away from the unusable and imperceptible region because they are just purely wasting energy. And we want to wisely budget the energy usage in the tolerable region according to performance requirements. And this is the information that we ideally want to convey in our application to the online system to better guide the online system to save energy. And to be able to express such information in a programming language, we really have to extract key pieces of information and to design succinct language abstractions for them. So we propose two abstractions that capture this information to the first order. The first abstraction is the performance, is a metric of the performance on the x-axis. So in an interactive application, the performance metric really comes down to one of the two forms. It is either the latency of a particular frame or it's a throughput of a sequence of frames. So for example, if a user interaction triggers an animation, which is a sequence of frames, a commonly used performance metric is FPS, frame per second, which is actually a throughput metric. So we call this abstraction QoS type because intuitively it is the type of QoS the users use to evaluate their experience. And the second abstraction is the two threshold performance values that separate the three QoS regions. And we call this abstraction QoS target because intuitively it is the performance target that the online system needs to deliver in order to ensure certain types of QoS, certain level of QoS. Now obviously we have two types of QoS targets. One is the imperceptible target on the right, and then the other is the usable target on the left. Now with the knowledge of these two QoS abstractions, what I want to talk about next is how do we actually express them in a programming, in a web application. And I'm going to do that using a running example. So this is pretty much one of the simplest web applications that one can ever come up with. But it does illustrate some key components of a web app. First of all, there's a notion of elements. For example, we have a div element here. Each element corresponds to a particular visual region in your application. Each element can be associated or registered with a set of events. For example, we're registering a touch end event with this div element. And each event is in turn associated with a callback function. For example, we are associating this anime move callback with the touch end event. And this callback function will be executed whenever the touch end event is triggered on the div element. Now, obviously doing this anime move callback execution, it's going to generate some animation. So overall, mobile web applications are executed in this event-driven manner, where an event being triggered on a particular element is a basic unit of execution. So the point here is that the event-driven nature of these applications really require us to express quality of service at an event level. And here's how we can express it. So the first step is to express the name of the element and the name of the event. For example, we're expressing the div element and the onTouchEnd event. And the second step is to specify two values. The first value for the QoS type and the second value for the QoS target. Now in this particular case, because the touchEnd event is going to trigger an animation, which is a sequence of frames, and therefore the QoS type is going to be throughput. As for the QoS target, you could either specify a numerical value such as 30 FPS, or you could qualitatively specify whether you can tolerate low performance or you have to guarantee high performance. And for both low and high, we're going to apply some default values for you, which is the case here. So if you are familiar with CSS, you realize that what we're really doing here is to define a new CSS rule. Of course, we had to extend the CSS syntax to be able to do that, but this new rule is fully compatible with CSS specifications, and so it's intuitive for developers to understand and to use. So there are two key features about this GreenWeb language annotation that I like to emphasize here. So first of all, if a developer wants to get rid of the old implementation of anime move and replace it with a new animation implementation, he or she can do that without touching the GreenWeb annotations. And this is because the language extensions do not specify or do not impose any constraints in terms of how the animation needs to be implemented, as long as it's an animation. So this means that the GreenWeb language annotations are implementation independent, which is actually a very important feature to have, because most of the web applications extensively rely on external libraries, whose implementations are out of your control and they get constantly updated. So it's important to be implementation independent. And secondly, if a developer wants to get rid of the QoS annotations altogether, he or she can do that without touching the rest of the program. And this means that the GreenWeb language extensions are actually not interfering with respect to functionality. Or in other words, the concern about QoS or energy efficiency is isolated from the concern about functionality. So now you know how the language extensions look like. What I want to talk about next is how do we actually annotate existing web applications. And what I've just showed you in the previous slide is sort of a manual annotation process where you as a developer has to sit down, take a look at application, manually inspect all its elements, and for each element you have to manually identify all its event callbacks, and for each callback you have to figure out what's really going on in that callback function to be able to determine the QoS annotations. And obviously that's a very tedious process, and ideally we would want an automatic annotation process. So we develop a system called AlBassam, which automatically inserts, well, it reasons about and then inserts GreenWeb annotations for you. In the paper, you can find implementation details about AlBassam, but due to time limit, I'm only going to show you a high level. It's a high level overview of how AlBassam works. So the way it works is that first of all, it has to translate the original program, web application, into a DOM tree. And you can think of the DOM tree as a true representation of the original web application, where each node on the tree corresponds to a particular element. And then we traverse the DOM tree and manually and then instrument all the callback functions of all the DOM elements. And then we synchronously trigger all the event callback functions. And during the event callback function execution, we have logic to detect the QoS information. And once we've got the QoS information, we can generate the annotations and simply produce the new program. And this is a high-level walkthrough of how AlBassam works, but you get the idea. Okay, so that's all about the language extensions. We know how it looks like. We know how you can annotate an application using these language extensions to express quality of service information. What I want to do next is talk about a runtime design that takes the QoS information and tries to save energy whenever possible. So at the very high level, here's what the GreenWeb runtime will have to do. Technically, a GreenWeb runtime is still part of a web browser. It just knows how to handle GreenWeb specific annotations. So what browser is doing is that whenever an input event is coming in, it receives, handles, and goes through a sequence of processing to produce frames, because frame updates are what ultimately perceivable to end users. Now, obviously, with GreenWeb, each event can be annotated with some QoS information. So the high-level objective of a GreenWeb runtime is to take the QoS information at the event level and to enforce it at the frame level in an energy-efficient way. Or in other words, it has to figure out how do I generate frames using the minimal energy but still satisfying the QoS specifications. So, for example, for that particular event, its QoS type is annotated as latency. Then the GreenWeb runtime knows that for this particular event, it is only going to produce one frame. And for that particular frame, because the QoS target is 16 milliseconds, then the GreenWeb runtime knows that I will have to be able to produce that particular frame within 16 milliseconds while using the least energy. Now, if the QoS type is annotated as throughput, then the runtime knows that for any subsequent frames that are associated with that particular input event, they all share the same 16 milliseconds QoS target. Of course, as time goes by, users are going to generate more events. And let's say for a new event, its QoS target is 2 seconds. Then the same process applies where the GreenWeb runtime knows that for that particular frame associated with the new event, its QoS target, its performance target is 2 seconds. So if we take this abstract view, we'll realize that what the GreenWeb runtime really has to do is actually two things. First of all, it has to be able to associate frames with the event. Or in other words, it has to be able to identify the set of frames that are responsible for a particular input event. And it's important to do so because if we do not do this correctly, we may end up assigning the wrong performance target to a particular frame. And once we've identified the associative frames, we will have to be able to schedule the frame execution or to deliver frames using the least energy while still satisfying the QoS target. So in the rest of the talk, I'm going to talk about these two steps step by step. So first of all, frame association. So to be able to understand, to associate frames with a particular input event, we really have to have a deeper understanding of how a frame is actually produced. Now, once the input event is received by the web browser, it has to go through a sequence of processing to produce the frame. Now, I'm not going to go into the details of any of these processing stages. For now, it's just enough for us to understand that a sequence of processing is actually involved, and I'm going to just simplify like this. Now, the complexity really comes in as soon as we realize that any modern browser is actually multi-process. For example, the input event is actually received and handled by the browser process. And these 5 processing stages are handled by the renderer process. And there's a GPU process that's dedicated to produce a frame. Just to add one more level of complexity, the 5 processing stages are multi-threaded. Here I'm only showing you 2 major threads, but in reality, many more threads could be involved. And these processing components talk to each other via a set of inter-process and inter-thread communication messages. And if more frames are generated from one event, they are further chained using these communication messages. So the idea here is that once we take this abstract view of how frames are processed, we can quickly realize that to associate frames with a particular input event, we just have to start from the root event, and then follow all these communication messages until there are no more messages. At that point, we've identified all the frames associated with a particular input, and then we can propagate the QoS information along these communication messages, and that's how we assign QoS information to each frame. And it looks straightforward, but it really requires us to understand these internal working mechanisms to be able to do the frame association. Now, once we've done with the frame association, the next step is to actually figure out how to actually deliver those frames while saving energy. Before I talk about any details, I want to say that GreenWeb doesn't actually, the language extensions do not impose any constraints in terms of how you save energy. In fact, it supports a range of energy saving techniques. So there's a lot of interesting research recently in the mobile computing community where they propose techniques like dynamic resolution scaling, power saving, using power saving colors. All of these fantastic ideas can be used as the underlying mechanism for a GreenWeb runtime to save energy. While most of these techniques are actually software-based by and large, we propose a runtime design that leverages a particular hardware mechanism called ACMP. ACMP, or asymmetric chip multiprocessor, is also known as a big data architecture. It is an emerging energy-efficient hardware architecture increasingly adopted by today's mobile vendors. So the big data architecture consists of a set of big cores and a set of small cores. Now, big cores are energy-consuming but high performance. Small cores are energy-conserving but low performance. And each core has a set of frequency settings. So the big data architecture really provides us a lot of flexibility to make trade-offs between performance and energy. And it is actually widely adopted in today's commodity mobile devices. If you are using a Samsung S6 or S5, it is actually powered by an ACMP. So the idea of an ACMP-based GreenWeb runtime is to identify a configuration, execution configuration, that provides just enough energy to meet the QoS constraints. So let's take this line of annotation as an example. The QoS target here is 16 milliseconds. And assuming that the 16 milliseconds line is over there, what the GreenWeb runtime will have to do is to identify the configuration pointed by that particular arrow, because that's a configuration that consumes the least energy while providing enough performance. So the way we do that is to leverage a technique called event-based scheduling, which is actually proposing our prior work. While I encourage you to read our original paper, I'm going to give you a high-level overview of how event-based scheduling works. So the idea here is that we want to be able to construct models that predict the execution time and energy consumption of each of these configurations. Once we know the execution time and energy consumption of all configurations, we can easily pick the configuration that consumes the least energy but provides enough performance. The way we model the execution time is to view the execution time as 2 components. One is the memory access time, and the other is the CPU execution time that's not overlapped with the memory access. And the CPU execution time can be further expressed as a number of cycles divided by frequency. So then we have a model between execution time and frequency with 2 unknown variables. We can profile this execution using 2 different frequencies and solve the system of equations and get an execution time model. Once we've got the execution time model, we can simply multiply that by power to get the energy model. and the power numbers can be profiled offline. And this is how we actually construct these two models and to correctly pick the optimal configuration. So I've showed you how the language extensions look like and how we can design a runtime that takes the language extension which expresses QoS information and tries to save energy. Now I'm going to move to evaluation. So we implemented and evaluated our system on real hardware software setup. The hardware setup that we use is the Odroid dashboard, which contains an SoC that's actually used in Samsung S4 smartphone. We integrated the GreenWeb implementation into Google Chrome browser running on top of Android, and we used a tool called Mosaic, which is developed in our group that allows us to do UI level recon replay to ensure reproducible results. So we compared GreenWeb against two baselines. The first baseline is perf. It's always running at the highest performance, and it's actually the standard policy to guarantee responsiveness in interactive applications. And the second baseline is interactive, which is the default CPU governor used by Android. So if you have an Android phone and if you don't do any change to it, that's the default setting. We primarily use two metrics. One is energy saving, which is straightforward to understand, and the other is QoS violation, which is defined as the percentage that a particular QoS target is exceeded. So for example, if the QoS target is 1 second and the actual execution is 2 seconds, then the QoS violation would be 100%. The applications that we use for evaluation is actually a mix of real hot web pages such as Amazon.com and also web apps based on popular frameworks such as to-do list app. So in this figure on the y-axis, I'm showing you the energy consumption normalized to perf. Recall that perf always runs at the highest performance and therefore it has the highest energy. So what we can see is that the interactive mode, it consumes almost the same energy as perf. And this shows that it almost always runs at the highest performance. On the contrary, GreenWeb is actually able to achieve a significant amount of energy savings. And the reason is because it understands QoS information, and therefore it's able to wisely budget the energy usage. Of course, the energy savings would be meaningless if the QoS violations are high. Now in this figure, I'm showing you the additional QoS violations that GreenWeb and Interactive introduce on top of perf. Recall again that perf runs at the highest performance and therefore has the lowest QoS violation. So what we see is that in many cases, GreenWeb actually does not introduce any additional QoS violations. So this means that in many cases it performs just as well as perf as far as QoS violation is concerned. And the highest QoS violation that GreenWeb introduces is only about 3%. So overall, we can achieve about 30% to 66% energy savings with only about 0.8% more QoS violations. So in summary, I just talked about GreenWeb, which is a set of program language extensions for balancing energy efficiency and quality of service in mobile web computing. It is based on a set of programming language abstractions that allow developers to express quality of service information. The runtime takes the QoS information as hints and tries to save energy whenever possible, as much as possible. By having the web developers and the web browser runtime work with each other, we can actually achieve a significant amount of energy savings. So we actually open source the implementation of GreenWeb, and you can find the source code on this awesome website we just built, whatwiseweb.org, along with many other cool stuff. So with this, I'd like to thank you for your attention, and I'm happy to take questions.
This is a great talk. I'm wondering, so you can specify with GreenWeb how event handlers should treat energy requirements, right? But what about JavaScript features like set timeout? If one of those event callbacks queues another callback up to happen later, how does GreenWeb treat that?
So if it's set timeout, and if you're using timeout to implement animations, right? So the way that GreenWeb views QoS is by frames. So if you're using timers to implement frames, right? Then for one particular event handler, if it's going to generate multiple frames, then you can still specify that as throughput. You can either use timers to implement animations, or you use CSS transition to implement animations. As a developer, you just have to know that this event callback is going to trigger an animation which generates a sequence of frames. It doesn't matter whether the animation is implemented by timers, right? So what you're saying is the callback will actually trigger a timer, and that timer might just trigger another timer, right? And then during each timer callback, you are generating a frame. So from GreenWeb's point of view, this event, the original event, is going to trigger a sequence of frames. You just have to specify that this event, the QS type is throughput. And if you have timers, right, they are still connected by the inter-process communication messages. So the runtime will still be able to keep track of all the chained timers.
Thank you.
Hi, I'm Manish Sridharan from Samsung Research. So for your evaluation, maybe I missed it, were the quality of service specifications written by hand or were they inferred?
The QS violations, so in this particular, so as a developer, you can always manually specify that, but in our evaluation, we use some default values. For example, if you are loading a web page. So in this evaluation, we're using some default values. For example, if you are triggering an animation, then the QS target could be 60 FPS or 30 FPS. Or if you're loading a web page, then the event latency could be 3 seconds or 1 second. In this particular evaluation, we use the standard default values for this particular evaluation. But obviously, you could specify that.
Right, yeah, I guess my follow-up question would be, how did you know that those default values were reasonable for these sites? Like, did you actually look at it, load it on the phone, and see that the performance was still okay?
Right, so these default values, we actually did a pretty comprehensive survey on HCI Darais. For example, FPS with 30 FPS and 60 FPS, these are two typical threshold values to guarantee sort of imperceptible user experience and tolerable, right? So these are standard values. And for web page loading, 3 seconds and 1 second, these are kind of two standard values that users use to evaluate their experience. These are what we got from a comprehensive HCI related survey. So, and then you can actually look at the video. We kind of manually watch the video and they make sense to us. So.
Okay, thank you.
I'm Anis from the Chrome team. Do you think the browser would be able to come up with the right performance mode to save energy? When the compositor is compositing chronos,
right.
It is rendering in 60 milliseconds, or when a page is idle, it's idle or loading.
Right. So if you're from Chrome, you know this Rail model.
Yeah.
Right. So the problem with Rail, well, not the problem, just one caveat of Rail is that it's difficult for the browser to automatically reason about whether it's ROA or ILL before an event callback is actually executed. Sometimes you really have to wait until the callback execution is finished to be able to tell whether this is an ROA or ILL. So what we're doing here is that we have developers to manually specify whether this event is going to be R or A. So in some cases, it's pretty straightforward to tell whether this is a throughput or latency, but there are cases where you really have to have the developers to come in and provide hints in the context of Rail. So.
We're currently working on that. We should chat.
Oh yeah, I work with Snag, so.
Awesome.